I will do a recap of three-phase systems. First of all, what we look at is the generation of three-phase EMF. So three-phase EMF stands for electromotive force. So to start off with, we use a very simple device or a very simplified setup whereby you have two poles, a north pole and a south pole, creating a magnetic field in between, or a space which is left that has an electric field that looks like that. And of course, you know, magnetic field moves from north pole to south pole. So that is the direction of the magnetic field. So that magnetic field, in it, you have a set of loops. So you have a simple conductor. This first one represents the cross section, and this represents the view from overhead. So overhead, you can see you have a loop of a conductor that is able to carry current, either a copper conductor or a wire or some such, and it is located inside a magnetic field, with the magnetic field going from left to right, north to south. So what then happens is, if you have a motion, so in that direction, if you move conductor material, the loop within the magnetic field, you will tend to have some interaction between the conductor and the magnetic field. So in our overhead view, it is as if this part moves up and this one moves down into the screen. So in our setup, you don't just have one loop, you have three sets of loops. So you have this first loop, R, R1, which are connected to each other, and it is shown on this side. Then you have B, B1, and Y, Y1. Right? So you have an electric wire or a conductor that is capable of carrying electricity being rotated inside the magnetic field. So what then happens once you rotate a conductor that can carry current within a magnetic field? You have the induction of an electric voltage, right? So the interaction between the motion, number one, the magnetic field, number two, creates, number three, an electric voltage or an electromotive force, which is what we are talking about here. Now, what you will then see is that the creation of the electromotive force will be dependent on the right-hand rule. This is your right-hand rule. So if you put the fingers of your right hand in the configuration shown such that they are all at right angles to each other, so that the thumb is at right angles to each of these. So the thumb is at right angle to the first finger or the forefinger or the index finger, and that in turn is at right angles to the middle finger or the center finger, so that they are all opposing each other. That will mean that if your thumb is pointing in the direction of the motion, in the case of this first diagram, it is pointing towards the right, as per what we see here. You orient your index finger in the direction of the magnetic field, which is now in the opposite direction, which is in that way, that direction, and then it will be able to show you the direction of the induced current. All right. So if you are to look, for example, on the overhead view here, all right, our motion, if you take the R1 arm, the motion, when you look at the screen, the motion, you will point your thumb towards yourself and away from the screen. You will point your index finger from left to right, so you point it towards your right, and you will find that your middle finger is left in an orientation such that it is pointing upwards, which is the direction that we show here. The direction of the electromotive force in blue, like that, because you have your motion going outward, your magnetic field going towards the right, which is there, and then you have your EMF going upwards in that direction. Similarly, if we look at it on the left-hand drawing from the cross-sectional view, you would find that the motion is pointing, and then you have your electromotive force as if it is going inside in that direction. Okay, and usually we denote a cross-sectional electromotive force that is going into the screen with a dot and coming outwards with an X. So what does this mean? Yeah, by the fact that you can have the interaction between a movement and a magnetic field inducing an electromotive force, you can make use of this, our ability to generate electrical power, because what we have done is you have converted the motion and the magnetic field into a voltage. And this is the principle of your generator. Your generator will create electrical voltage or electromotive force if you have a movement within, or rather within, a magnetic field. So now if you were to put in three sets of current carrying conductors at different angles to each other. So like if you take the R side of the conductor as the primary one, you put in on the same axis another current carrying conductor at an angle shown. So that angle here, the angle in between the R and the Y, will be 120 degrees, and the angle between R and B all the way over here, this will be 240 degrees from R. Okay, so the angle between the main axes, so if R is the main one, then you have Y, then you have B, every one of those will be 120 degrees apart from each other. Okay, so when you mount it in such a configuration, your EMF will tend to look like this. Reason being, if we take your red voltage like that, yeah, the movement of your conductor through the magnetic field changes the magnitude of the electromotive force. So let's take an example of different points. So the conductor is rotated through, we've said that it moves, it is free to move within this magnetic field. So your conductor, what will happen? Let me clear up this. Is free to move. So like you are winding R or your conductor R, it is free to move throughout this space along the axis that is indicated. So here is your axis, all right? So it will rotate in this direction. At this particular point that we were initially showing, if you take this point where the conductor is, and you see that it is moving in that direction, the direction of the magnetic field is here. If you try to look at, even with your fingers with the right hand rule, you will notice that the motion and the field are directly opposing each other. Okay? Therefore, at this particular point, when it is oriented here, your EMF is 0 because they are opposing each other. But let's take an orientation, same R conductor. It is moving around the same axis, so it is in this direction. But at this particular instant, when it is in this orientation, its movement is there. And at this particular orientation, once again, your magnetic field stays in the same way at that direction. Okay, so then what you have is, you have the forces that are acting on your point R are the magnetic field in that direction and your motion in that direction. So they are not exactly at 90 degrees to each other. So the action as indicated by the right hand rule will not be exactly maximum, will not be at its peak, but it will have some element of it. So you can even resolve the forces that are acting on that particular point due to motion. So you have the resultant, or the actual in the direction that we are looking at, will be some angle theta, or rather will be force due to the motion times the cosine of that angle theta. And that would mean that if say it was at this particular point in time, you have the value of your electromotive force, which is here, is less than what the peak would be, but it is also more than what the minimum would be. If we were to further now illustrate or pick a point whereby your conductor has rotated through its axis, whereby it is now moving in that direction and the magnetic field is still in the same direction, the forces that are acting on your point R, this is the same R, but it has moved from this configuration, that angle, to become now horizontal in our diagram. Yeah. So that now the magnetic field is in that direction and motion is now perpendicular to the magnetic field, so that now the right-hand rule fully applies in this case. So the interaction between the magnetic field and the motion are at right angles to each other when in this configuration. And that configuration then is represented by the peak, as you show it here, right? So at this point, which we can call the peak, you have the maximum possible electromagnetic force that you can get out of this configuration. As the conductor now continues to move, let's say it reaches that direction, as it now continues to move, it then has a resultant EMF that is different, or that is less than the peak. This concept is there throughout. You've seen it in DC generators. You've seen it in various other forms of electromagnetic machines, whereby you have a motion of a conductor within a magnetic field that creates an EMF. That process, we have said, is called induction, and it is through induction that we have electromagnetic force being created within an electrical machine. This is the basic principle by which all generators operate. And the reason now why we have 3 sets of curves is because if you are to have 3 current carrying conductors mounted on the same axis as we have shown here, and they are rotated around that axis at the same speed, but they are 120 degrees apart from each other, they will interact with the magnetic field in the same way that we have illustrated. However, their interactions with the electromagnetic field will be 120 degrees apart from each other. So if, for example, your red conductor reached this point at time 0, the Y or the yellow conductor will reach this point 120 degrees after that. It will have to rotate through 120 degrees in order to reach that point. And that is illustrated here by the fact that if R at this point and this point in time has an EMF of 0, 120 degrees later, Y, which is represented by this dashed curve, will reach the same value of 0 EMF. And then 120 degrees after that, you will then have B, or blue, which is represented by this dotted curve, reaching the same point because they are mounted 120 degrees apart from each other, which we have already seen. Okay, so that 120 degrees separation is what gives these differences in electromotive force. And these differences in electromotive force, these lags, yeah, because it is lagging behind. It takes 120 degrees for the yellow to reach the same point where red was. These lags are what now create a 3-phase voltage, right? So a 3-phase voltage is similar to having 3 different sources of voltage related to each other and matching each other. It is as if you were to have 3 batteries that would produce AC instead of DC, and you would be able to have connections between them. So that's the principle of three-phase power or three-phase EMF. They are always 120 degrees apart. They are always mounted on the same axle, and they always have an interaction between each other because they experience the same magnetic field from each other. Now let's take this analogy a bit further. So we have said you can think of them as three different windings or three different sources that are mounted on the same axis. So if you were to make this instead of a single loop, you have it as a set of windings, you would be able to generate much more voltage. So windings, we will represent them with this coil. So let's take the case whereby you have sources or these windings being connected up to a load. So a load can be a bulb, a motor, or whatever it is, and they are supplying AC. So for this analogy, let's assume that our battery here is able to supply AC, and we have three batteries that kind of are connected next to each other. Okay, let's call them the red one, the blue one, and the yellow battery. Now if you were to put three batteries together, if you had three batteries next to each other, you have a number of options to connect them together. You can have them in parallel to each other, whereby you would have them one next to the other, like that, and then you would be able to, say, connect them, loop them like that. So in this case, what would be the voltage that you would get if you connect them like that? What is that voltage V? Of course, the voltage V, because they are connected in parallel, so it's 1.5 volts. But if we were to put them in series with each other, which is connected to each other one after the other, okay? If we were to connect them all together, you would then have the sum of each of them. So it's 1.5 plus 1.5 plus 1.5, which would be 4.5 volts. And the same kind of principle would apply in the case of three-phase voltages, whereby if you were to add up the three of them, so in order for us to do that, we usually take the start and the finish of each. So the voltage in this case would be labeled EB1R, and that would be the sum of EB, EY, and ER. Okay, EB1R, which is this point here and that point there, the 2 points through which they would be next to each other. Now, in order for us to do that, we would add them up by saying that EB1R is equal to EB plus EY plus ER, the sum of all three of the voltages. But what are the representations of these voltages? EB from here is represented by a sine wave, all right? So it is the sine of angle theta times the maximum value. Yeah, this curve, its maximum value, we can call it EM, the maximum value, and it is common to all three of our voltage sources. So in this case, red or the R voltage would be represented by ER is equal to EM, the maximum, times sine theta, which is that, because the angle through which it goes is sine theta. Sine of 0 is 0, so the EM at this point is 0. However, EY, because it starts, it has a lag of 120, it has the same peak, EM, but it is sine of theta minus its lag, which is 120 degrees. Likewise, EB would be EM sine theta minus 240, which is our gap from there to there. Now, if we add up all these together, so you have EM sine theta plus EM sine theta minus 120 plus EM sine theta minus 240. Let's group them all together. You find that they will end up by a series of trigonometric identities looking like this. Sine theta. So sine A minus B changes to sine theta cos 120 degrees minus cos theta sine 120 degrees, and that one expands to, continuing with this expansion, it would be, now we notice a number of terms that will start to cancel each other out. So this and this will add up to negative sine theta. We already have sine theta. And then you have this and this cancelling each other out. So you will end up with EM sine theta minus sine theta. Ultimately, this becomes a 0. So what does that imply? It means that when you connect three-phase voltages that are mounted on the same axis, this sum total, there's no net voltage between these 2 points, which means that this point and this point are at the same potential. So it means you could actually connect up these 3 different windings internally without there being any flow internally. You would still get voltage or current flow through your loads. Yeah, these individual circuits are loops in themselves. Okay, remember, to connect a load, you have 2 points. You have a source connected to a load. But if you connect all 3 of them internally here in the windings, if you call this your generator, internally here you have no resultant electromotive force. This is very important in the next stage, whereby we look at 2 different connections of conductors or connections of machines. The first one is called the delta connection, whereby you take each of the windings, red, yellow, and blue, and you connect them in that configuration, whereby you have the battery concept that we had. You connect start to finish, start to finish, start to finish, and then you loop back and connect the finish of one to the start of the other. And then you would be able from each of them to have loads being connected in between. And we call these conductors phases. These are the different phases of each of them. Okay? And that's why we say we have 3-phase power. Another way of looking at it would be if you were to connect them in this configuration. That's why you call it a delta. Okay? You have one winding, the red that we initially started with, connected to the yellow, and at the same time connected to the blue. And the blue and the yellow are connected to each other, and you have your phases that look like that. Incidentally, in Kenya, the phases themselves, we have either 415 or 240, which is what we'll look at shortly. Okay, so this is what you call a delta connection. That's one option. The second option of connection is called a star connection, whereby you connect all the starts, this one, and this one together, and you connect all the finishes to the other side of the conductor so that they will look like this. Okay, so it will be as if, let me put it in another way, if you were to connect your windings, and these finishes would be your phases. Then these starts form what is called the neutral. So you have your winding, let's call that red, let's call that blue, let's call that yellow. All the starting points of your windings, you connect them up together, the joined up parts of the windings, will be connected to what you call the neutral. So what you now end up with is you have 3 phases and you have what you call a neutral wire. And this may start to be familiar to you in that usually when you have power being transmitted, you will usually see either 4 wires, or you will see, for very high voltage connections, you will see 3 wires or 3 phases. And this is what we are representing here. 3-phase voltage can be either transmitted or connected in a delta connection, that is 3 wires, or if you have it in a star connection, it will be connected in 4 wires. So this is a 4-wire system, and the delta connection is a 3-wire system. Let's start with the currents. The currents within each of these windings and the voltages are in 2 types. So if you have your machine and it is connected to your loads, let's call these your loads, it is connected via these cables, okay? So inside the generator, any currents or voltages are what you call the phase voltages. So like if you go back to your individual generators, when you have your windings that are connected internally within here, the voltage that is available, so let's say EY here, the voltage at this point, yeah, before you take it from the machine, this kind of voltage is called a phase voltage, because that is the voltage that is seen by the windings themselves, right? On this other side, the voltage in between the two, when it goes to the load side, is called your line voltage, all right? 2 different concepts, a phase voltage and a line voltage. Similarly, the current that will flow through, we usually denote current with I, the current that will flow through the windings is called the phase voltage, and the current that will flow through the load is called your line current, I line and I phase. So it is essentially V phase and V line, or you have I phase and I line. Going back to our delta connection, so the delta connection here, you will notice that your phase voltages, which are these ones, phase voltages here, are the same voltages that the load will see. So in the case of delta, phase voltage is equal to line voltage, right? Because they are constituting the same thing. If you look at it from this point of view, this makes it even easier to look at. Your voltage here, EY, for example, is the same as here, okay? There is no difference, yeah? These connecting points on either side, the voltages are the same. So phase voltage is equal to line voltage in the case of delta, okay? However, look at the currents that are flowing through the delta windings or the delta machine. So if we were to redraw it a bit, so this is going towards your load. The current that is flowing will not be the same as the current that is flowing here. The reason for that is the sum of the currents flowing into a point must be equal to the sum of currents flowing out of a point. So in this case, the currents flowing into the point are IY, and the currents flowing out of it are IL and IB. So you will realize that these currents are not equal. The phase currents, which are these ones that the winding C, are not the same as your line current, okay? Now, there's a reason why this and this and this add up to each other. In summary, the line current of delta will be equal to root 3 times the phase voltage, right? So because you have currents that are flowing within your machine and they tend to flow into each other and add up to each other, they are different from the currents that will flow out of your machine. Remember, this is your machine and the points at which it flows out are the load or the line currents. So IL is here, and these currents that are flowing here, are the phase currents. So you have line current in delta is equal to root 3. We won't go into the calculations right now, but you can see them in the text that I have shared. In the end, you have root 3 of I phase. So this is the delta situation. Phase voltage and line voltage are equal. Line current and phase current are not equal. So for delta, we have said IL, line voltage, is equal to root 3 times I phase. And that is the case for all of them. And we have said line voltage is equal to phase voltage. Okay. So let's look at the case of our star connection. So you have your generator or your machine there, and you have your loads. So what are the voltages that are seen? The voltage that is seen in the windings or in the machine itself, which are the phase voltages, are there. All right. So the phase voltage is this point for the red and that point. And you will notice that this point is the same point as here, because this is just a conductor. So it is there. And this point is the same point as your neutral. Yeah, remember we said there is a connector, or there's a wire that you can pull out to create your fourth wire, which is your neutral. So the phase voltage is between a phase here and a point here. This is V phase. Yeah, and one end of this is the neutral, and the other end is your line into the load that goes towards the load. Okay, so your phase voltage is between a neutral and a line. Now for the loads themselves, the same thing will tend to happen. You will have them be connected between a line and a neutral. But what about the line voltages? That is the voltage between here and here. Yeah, this is your line. Okay, what is going out? What will this connection look like? You can see it is very different from this one because it is between one phase and another phase. Sometimes you call it the V phase to phase. Okay, this line voltage is very different from the phase voltage. And we usually say line voltage in a star connection is equal to root 3 times phase voltage. But in a star connection, the currents that flow through are all identical, right? Whether it is flowing through the winding or flowing to the load, it is the same current, okay? So because of that, we say line current in a star connection is equal to the phase current star connection because they are flowing through the same place. So IL is equal to I phase and VL is equal to root 3 times V phase. One interesting concept in Kenya, our phase voltages are 240 volts, right? The voltage that you get when you connect your charger to the socket is 240 volts. And an interesting thing you will see is 240 times root 3 will give you 415. And if this figure looks familiar to you, it is because 415 is the line voltage of cables that are supplying power.